Okay, good day. For our discussion this week, we're going to have the linear programming. Okay, so what are our objectives for today? So, number one, discuss the basic concepts of linear programming. Number two, determine the applications of linear programming. Number three, use the graphical method in linear programming. And then lastly, solve problems using graphical method in linear programming. Okay, so by the definition, let's look back. Let's have the origin of this concept of this linear programming. So, initially, by the definition, linear programming is a method of dealing with decision problems that can be expressed as constrained linear models. It is a mathematical technique for finding the best uses of organizations' resources. So initially, this one, it was invented in the 1940s by George Danzig. Okay, and it serves as the result of military research planning on how to distribute the men, the weapons, and supplies efficiently to the various fronts during the World War II. So initially, this concept is intended for the war during the World War II. But nowadays, linear programming is essential, is useful when it comes to businesses. Okay, so linear programming is an optimization technique for a system of linear constraints and a linear objective function. Okay, so here we need to recall the concept of the linear equation and linear inequality for us to solve, for us to proceed with the concept of the linear programming. So linear equation is a in a two variables x and y is an equation that can be written in the form of ax plus by is equal to z, where a, b, and c are constants. Such equation is referred to as the linear equation because its graph is a line. While the linear inequality, again in two variables x and y, is an inequality that can be written in the form of ax plus by greater than c, or with other inequality symbols such as less than or equal, greater than or equal, instead of the equal sign. Okay, so a linear inequality is the result of replacing linear equation equal symbol with an inequality symbol. Okay, so now let's have a recall. Okay, let's have a recall on how we graph, okay, linear equation and linear inequality. And before that, let's have the different concepts to consider when it comes to the linear programming. The first one is the optimization. It is the maximizing or minimizing a quantity. So our goal here uh, is to maximize or to minimize, okay, to efficiently use our available resources. For instance, when it comes to the war, okay, so they are utilizing the uh, distribution of the men, the weapons, and their supplies for them to win in a war. And also, nowadays, it could be applied to the manufacturing when it comes to the labor and the machinery cost of operations in different businesses. Objective function, it is a function that mathematically describes the profit. It describes the profit. So when it comes to objective function, we're going to use the linear equation. And then for the constraints, these are the restrictions of the given problem. Okay, so here when it comes to the constraints, we're going to use inequality symbols for us to limit, okay, our available resources. And then lastly, the corner principle. It is the maximum and the minimum values of the objective function occur at the corner points of the region of possible solutions if the region is bounded. So when it comes to identifying the values for us to maximize or minimize the quantity that is needed in our problem, we're going to use the corner or the ordered pairs. Okay, for the feasible region. Okay, so the feasible region refers to the intersection of all the shaded region of our inequalities. So in linear programming model, we have here for the objective function, we're going to use the equation. Okay, and then for the constraints, we're going to use the inequality symbols. Okay, so now let's have the recall. Okay, the recall of graphing the linear equation and linear inequality. Okay, so first off, let's have this. X plus y is equal to 3. So here, for us to graph this, we can have its slope-intercept form, or uh, just simply identify the intercepts. Okay, just simply identify the intercept. So the slope-intercept form of this is we have y is equal to negative x plus 3. Okay, so we have in general form y is equal to mx plus b. And this one, we have here y is equal to negative x plus 3. And then let's identify the intercepts. Okay, so to identify the intercepts, x-intercept, okay, all we need to do is to substitute y as 0, and we need to solve for the x. For instance, here, if we're going to solve for the x-intercept, we let y be equal to 0. So if y is equal to 0, we have 0 is equal to negative x plus 3. Okay, and 0 is equal to negative x plus 3. If we're going to identify the value of x, there is x is equal to 3. Okay, so therefore our x-intercept is 3 comma 0. Okay, 3 comma 0. And then for the y-intercept, all we need to do is to replace x as 0 and then find for the value of y. Okay, so if we replace x as 0, so y is equal to 3. So therefore we have here an ordered pair 0 comma 3. So the intercepts are 0 comma 3 for the y-intercept, and then for the x-intercept we have 3 comma 0. Okay, so if we're going to graph that, all we need to do is to plot the 2 points in our Cartesian plane, then we need to connect that. Okay, so here's what will happen. Okay, so we have here the 0 comma 3 as our y-intercept, and then 3 comma 0 as our x-intercept. And then all we need to do is to connect that. Okay, and then extend both sides. Okay, and then now we'll have the graph of the x plus y is equal to 3. Another example, let's say we have 2x plus 3y is equal to 12. Okay, so if we're going to use the slope-intercept form, we'll have 3y is equal to negative 2x plus 12. Okay, and then here, we can divide it by 3 to have its the slope-intercept form. But let's not just proceed with that. Okay, let's just identify the intercepts. Okay, so for the x-intercept again, we let y be equal to 0. So if we let y be equal to 0, so 3 times 0, that's 0. So 0 is equal to negative 2x plus 12. And then 0 is equal to negative 2x plus 12. Finding for the value of x is equal to 6. Okay, so we'll have the x-intercept as 6 comma 0. And then for the y-intercept, we let x be equal to 0. So negative 2 times 0, that is 0. So 3y is equal to 12. And 3y is equal to 12, that is y is equal to 4. Okay, so we have the y-intercept 0 comma 4 and the x-intercept 6 comma 0. Okay, so same procedure. All we need to do is to plot that in our Cartesian plane, and then we're going to connect it and then extend both sides. So here's what will happen. So we have here our y-intercept 0 comma 4 and then x-intercept 6 comma 0. Okay, so we'll have this. Okay, so connect the two ordered pairs and then extend both sides. And then we'll have now the graph of 2x plus 3y is equal to 12. Now, how about if we're going to graph the linear inequality? Actually, it's almost same, but for the linear inequality, we need to shade a specific region for us to satisfy that. For instance, we have here the x plus y is greater than 3. So as you notice, if we're going to have the equation x plus y is equal to 3, we have the solid line here. Okay, but this time, we have x plus y greater than 3. So as you can see, we have the symbol greater than, so obviously, we're going to shade the upper region. Okay, we're going to shade the upper region. And also, why is it broken line? So as you notice, we have here greater than 3. Since there's no equal symbol here, instead of a solid line, we're going to have a broken line. Okay, so the graph of x plus y greater than 3, we're going to have the shaded region at the upper part. And then, since it is greater than, we have the broken lines. Okay, we have the broken lines. Another example, let's say we have 2x plus 3y is less than or equal to 12. So as you notice here, since there's a less than or equal symbol, so we have this solid line. Okay, we have this solid line. And also, since this is less than or equal to, we're going to shade the lower part. Okay, we're going to shade the lower part here. Okay, to indicate that this is the less than or equal. Okay, for this linear inequality. Okay, so take note, if we're going to use a solid line here, it should be less than or equal or greater than or equal. And then if it is broken line, less than or the greater than. Okay, the less than or the greater than. Okay, so now, uh, take note. Okay, take note if we have the less than, we're going to shade the lower region, and then if we have the greater than, we're going to shade the upper region. Okay, so take note of that. Okay, so that is the only case that we're going to focus. Okay, so there are lots of cases to consider when it comes to the linear inequality, but this time we're just going to consider that case. Okay, so now, the word programming. Okay, the word programming means producing a plan or a procedure that determines the solution to a problem. Okay, so in our situation, in our problems that we're going to solve, we'll have this linear programming to have the optimization techniques. Okay, it is used in every day in our organization and allocation of our resources. Okay, we can have lots of variables, but uh, we're going to limit that. Okay, we're going to limit that to 2 variables for us to uh, have one case only. And then our approach here is a graphical solution method. Okay, it's a graphical solution method, which is a two-dimensional geometric analysis of linear programming problems with 2 decision variables. So take note that we're going to use Cartesian plane, okay, for us to identify the solution to our problem. And the theory of linear programming states that the optimal solution will lie at the corner points of the feasible region. Okay, so take note of that. So, now, in our discussion, we're going to have the manual way to graph, okay, the inequalities. Okay, but also for your supplemental material, you can use the Desmos. Okay, you can use the Desmos as your guide for you to have the graph of the linear inequalities in our problem. And in addition, when it comes to the Desmos, it will give you the uh, corner points. Okay, it will give you the corner points. All you need to do is to identify the feasible region in the given graphs. Okay, but again, we're going to show the two ways. One is using the manual way of solving for its corner points, and then the other one is using the Desmos. Okay, so Desmos is just your supplemental material. Okay, way for you to graph the inequalities. Okay, so we have here 5 steps in solving linear programming. The first step is list the independent variables. And then in step 1, always remember that we need to identify, okay, we need to identify the independent variables that is involved in our problem. Step 2, list the constraints and translate them into linear inequality. So take note, constraints are represented by a linear inequality. Okay, and those linear inequalities will be graphed later on in our step number 4. Then step number 3, set the objective function and translate it into linear equation. And then step 4, graph the feasible region. So we need to identify the intersection of all the shaded uh, parts, okay, on each inequalities. And then lastly, from that feasible region, we need to identify the corner points. Okay, we need to identify the corner points or the ordered pairs, and then we substitute that into our objective function for us to identify the value of the z that is associated with those points. Okay, so let's start. Okay, let's start our discussion here with problem number 1. Okay, in problem number 1, we have this. Let me read. A craftsman produces two products, coffee tables and end tables. And then we have the production of one coffee table that requires 6 hours of his labor, and the material costs him 200 pesos. While the production of one end table requires 5 hours of labor, and the materials cost him 100 pesos. The craftsman wants to work no more than 40 hours each week, and his financial resources allow him to pay no more than 1,000 pesos for each materials each week. Okay, for materials each week. If he can sell as many tables as he can make, and if his profit is 240 pesos per coffee table and 160 pesos per end table, how many coffee tables and how many end tables should he make each week to maximize the weekly profit? Okay, so in this situation, first we need to recognize the independent variables in our problem. Okay, so for you to easily identify that, all you need to do is to look at the given question at the end. Okay, so here we have the question about the quantity. Okay, the quantity of the number of coffee tables and the number of end tables. Okay, so with that, we can identify its maximum weekly profit. Okay, so from the quantity of the coffee tables and the quantity of the end tables that will be produced, we can identify the maximum weekly profit. Okay, so let's say we let X as the number of coffee tables made each week, and then let Y be the number of end tables made each week. Okay, so always remember you need to represent, okay, the independent variables. Okay, so let's say we have here X and Y. And then for step 2, we need to list down the constraints and translate them into linear inequality. So for you to easily identify those constraints, we can have the different factors to consider here. Okay, such as the production hours. Okay, and also when it comes to the material costs. Okay, for each coffee table and end table. Okay, so let's have this table. So let's say we have production, the number of hours, and then the cost, which is the materials. For the coffee table, it states that he needs 6 hours, okay, for coffee table. And then for the end table, it requires 5 hours. Okay, it requires 5 hours. In addition, it says that the craftsman wants to work no more than 40 hours each week. Okay, so again, the craftsman wants to work no more than 40 hours each week. Okay, so for us to uh, have this, we need to translate it later. Okay, that no more than 40 hours. Let's just include it first. The no more than 40 hours. And then for the material costs, for each coffee table, that's 200 pesos. And then for the end table, that is 100 pesos. And again, the financial resources allow him to pay no more than 1,000 pesos. It allows him to no more than 1,000 pesos. Okay? Let's include also the profit. Okay? For us to have the summary of our uh, problem. Okay? Though na that it is only that it is for intended for step 3. But let's just include that. Okay? So here we have this one. And then for the profit, it indicates that for each coffee table, he earns 240 pesos. And then for the end tables, he earns 160 pesos for each end table. And then for the total profit, we don't know that. So let's represent that as Z. Okay, let's represent that as Z. So now, let's have the representation of the production and the material costs. Okay, into linear inequality. So as you notice, the total per week should be no more than 40. Okay, and if we're going to translate that no more than, we can have the less than or equal. Okay, we can have the less than or equal. Okay, and then since we are after with the total, all we need to do is to have the sum of that 6 hours times its number of coffee tables plus the 5 hours times the number of end tables. Okay, so we'll have 6x plus 5y less than or equal to 40. So we have here again 6x, okay, to represent the production hours for the coffee tables. And then for the end tables, we have that 5y. Okay, and then the total for per week here is no more than 40, which is less than or equal to 40. So 6x plus 5y is less than or equal to 40. And then for the material costs, same procedure. 200 times its quantity of the coffee table, so 200x. And then 100 times the quantity of the end tables, which is y. So 200x plus 100y. No more than again, so that is less than or equal to 1,000. So we have here 200x plus 100y is less than or equal to 1,000. Okay, now, since we are after with a real life solution here with our problem in linear programming, we need to restrict the values of x and y. Okay, since x and y refers to the quantity of the coffee tables and end tables, it cannot be negative. Okay, it can be negative. So let's restrict the quantity of the coffee tables and end tables as greater than or equal to 0. Okay, again, since we are after with the real life, okay, with the real life solution here, for the quantity of the coffee tables and the end tables, we need to restrict the values of x and y. It should be greater than or equal to 0. Okay, we can have the negative values here. Okay, the next one, for step number 3, we have the objective function. So as we recall, for the coffee table, we have 240 pesos profit per coffee table and then 160 pesos per end table. So if we're going to represent that in a linear equation, we'll have that 240x, okay, which is the quantity of the coffee table, plus 160y, which is the quantity of the end table, is equal to the z. Okay, so 240x plus 160y is equal to z. And then now, let's have step number 4. We need to graph the feasible region. So for us to identify the intersection of all those shaded region, we need to graph it individually. So let's start first with 6x plus 5y less than or equal to 40. Okay, so here, for us to identify the graph of this, we need to have the intercepts. We need to determine the intercepts. So let's say we have here 6x plus 5y is equal to 40. Okay, and if you will recall, for us to identify the x-intercept, we let y be equal to 0. So we have 6x plus 5 times 0 is equal to 40. So in this case, I did not use the slope-intercept form. I proceed with the linear inequality. Okay, and its form. Okay, so we have here 6x plus 5 times 0 is equal to 40. And 5 times 0 is 0. So 6x is equal to 40. And 40 divided by 6, that is 20 over 3. So therefore, the x-intercept here is 20 over 3, comma 0. And then for the y-intercept, we let x be equal to 0. So 6 times 0, that's 0, plus 5y is equal to 40. And 5y is equal to 40, divide both sides by 5. So we'll have y is equal to 8. So therefore, our y-intercept here is 0, comma 8. Okay, so here, we're just going to plot this 20 over 3 comma 0 and 0 comma 8. And then we extend, we connect and extend both sides. Now, since we are after also with the linear inequality here, we have the less than or equal. So if you will recall, we said that if we have less than or equal, we have a solid line. And at the same time, the shaded region is in the lower part. Okay, so here's what will happen. Okay, the x-intercept, 6.667 or 20 over 3, comma 0. And then the y-intercept, we have 0, comma 8. Okay, then we connect and then extend both sides. And then as you notice, we have here less than or equal. Since that is less than or equal, we have a solid line. Okay, and in addition, since it is less than, we need to shade the lower part. Okay, the lower region here. Okay, to have the 6x plus 5y less than or equal to 40. The other constraint that we have is 200x plus 100y is less than or equal to 1000. So same procedure, we need to identify the intercepts. Okay, so for the x-intercept, we let y be equal to 0. So we have here 200x plus 100 times 0 is equal to 1000. And 100 times 0 is 0, so 200x is equal to 1000. So we have here x is equal to 5. So therefore, we have now the x-intercept 5, comma 0. And then for the y-intercept, we let x be equal to 0. So 200 times 0 plus 100y is equal to 1000. And then 100y is equal to 1000. We divide both sides by 100 and we have y is equal to 10, which is 0, comma 10. Okay, when x is 0, y is equal to 10. So we have 0, comma 10. So same procedure, we plot this 5, comma 0 and 0, comma 10. We connect them and then extend both sides. Then again, we have less than or equal. Since we have here a symbol of less than or equal, again, we have the solid line. And at the same time, the shaded region is in the lower part. Okay, the shaded region is in the lower part. So this is the graph. Okay, this is the graph of 200x plus 100y is less than or equal to 1000. And then for the next one, x greater than or equal to 0 and y is greater than or equal to 0. So notice when it comes to the Cartesian plane, the values of x that is greater than or equal to 0 or that is positive is in quadrant 1 and quadrant 4. Right? The values of x. So we need to highlight, okay, we need to shade the region of the first quadrant and the fourth quadrant here. Okay, so take note of that. And then for the y greater than or equal to 0, so the values of y that is uh, greater than or equal to 0, so that is positive also. That is in quadrant 1 and quadrant 3. Okay, so I'm sorry. Okay, so we have quadrant 1 and quadrant 3. So this quadrants, they have positive values of y. Okay, so we have here the shaded region, which is y is greater than or equal to 0. Now, after we have the graphs of the four inequalities, we need to combine them. Okay, we need to combine the four graphs and identify the feasible region or the intersection of all the graphs. So we have again the four constraints, and this is the uh, combination of all the graphs. This is the combination of all the graphs. So the black portion here it indicates the constraint 6x plus 5y less than or equal to 40. And then the green one, that is 200x plus 100y less than or equal to 1000. And the blue part is x greater than or equal to 0. And then for the red, that is y is greater than or equal to 0. Okay, so notice, here, we have different areas to consider. But again, we need to have the shaded region that intersects with all four inequalities. Okay, and here we have this area. Okay, all the other areas does not have the intersection of all the graphs. Okay, but in this portion we have the intersection of the four. Okay, now this is the feasible region. This is the feasible region. Now, for us to have the corner points, we need to consider the following. Okay, this part, this, this, and this. Okay, all the corner points. Okay, so let's proceed with the identifying the corner points here. Okay, so here, as you can see, we have 0, comma 0, so that is the origin. And then this one, we have the y-intercept. Okay, the y-intercept of 6x plus 5y less than or equal to 40. Okay, which is 0, comma 8. Okay, which is 0, comma 8. So again, this is the origin, 0, comma 0. And then we have here 0, comma 8. And then this one, this is the part of the constraint 200x plus 100y less than or equal to 1000. This is the x-intercept of the green graph, which is 5, comma 0. Okay, that is 5, comma 0. Now, how about this one? Okay, how about this point? So, here, actually, it's not the intercept. So, therefore, we need to have its point of intersection. Okay, of what? The two inequalities. Okay, which is the 6x plus 5y less than or equal to 40 and 200x plus 100y less than or equal to 1000. Okay, we need to identify its point of intersection. So as you notice, it's coming from the graph, okay, of the 6x plus 5y less than or equal to 40 and 200x plus 100y less than or equal to 1000. Okay, so now, for us to solve that, okay, let's transform it into equation. Let's transform it into equation. So we have 6x plus 5y is equal to 40. And then 200x plus 100y is equal to 1000. Okay, so let's say this is the equation 1. And then this is the equation 2. Okay, so here, you need to recall the concept of the system of linear equation when it comes to elimination or substitution. Okay, but this time I'm going to present to you the system of linear elimination. Okay, so here we need to eliminate one variable here. Okay, we need to eliminate one variable here. So we need to have a numerical value that is same for x or for y. Okay, so let's say we want to eliminate x. No, no. Let's say we want to eliminate y. Let's say we want to eliminate y. So since we have here 100y, and then we have 5y here. So think of a number that you will multiply to 5 that will give you the result of 100. So that is 20. So let's say we multiply 20 to equation 1. So here's what will happen. So we'll have, so 20 times 6, that's 120x. And then 20 times 5, that's 100y. And then 40 times 20, that's 800. So we have 120x plus 100y is equal to 800. That is equation 1.1. And then, again, we're going to eliminate y. Okay, so for us to do that, we need to subtract this equation 1.1 to equation 2. Okay, so let's subtract equation 1 to equation 1.1 to equation 2. So here's what will happen. We have that 120x plus 100y is equal to 800 minus 200x plus 100y is equal to 1000. Okay, so as you notice here, we have 120 minus 200, and we have 120 minus 200x, 120x minus 200x, that is negative 80x. And then 100y minus 100y, that is 0. Okay. And then 800 minus 1000, that is negative 200. Okay, so we'll have negative 80x is equal to negative 200. And then solve for the value of x. So divide both sides by negative 80. We'll obtain x is equal to 2.5. Okay, so x is equal to 2.5. Okay, so now we have the value of x of this corner point. But for us to solve for the y, let's substitute it to equation 1 or equation 2. So let's say we substitute it in our equation 1. Okay, so 6x plus 5 is equal to 40. Substitute that x is equal to 2.5. We'll have 6 times 2.5 plus 5y is equal to 40. Okay, and then simplifying that, 6 times 2.5, that's 15. Okay, by addition property of equality, or just simply transpose. So transpose that 15, that will be negative 15. So 5y is equal to 40 minus 15. And 40 minus 15, that is 25. And then 25 divided by 5, that is y is equal to 5. Okay, that is y is equal to 5. So therefore, the corner point here is 2.5 comma 5. Okay, so that is 2.5 comma 5. Okay, we just identify, okay, the point of intersection by using the system of linear elimination for the two linear inequalities. Okay, the 6x plus 5y is equal to less than or equal to 40, and 200x plus 100y is less than or equal to 1000. So therefore, in our step number 5, we have now the corner points. Okay, the 4 corner points. Okay, so the corner points of the feasible regions are 0, 0, 5, 0, 0, 8, and 2.5, 5. So now, we need to substitute the 4 points in our objective function. And earlier, our objective function is 240x plus 160y equals z. Okay, so let's just substitute x and y values here. So if we have x as 0 and y 0, so 240 times 0 plus 160 times 0, which is 0. So therefore, the profit here is 0. And the next one, we have here 5, 0. So if we're going to substitute that, 240 times 5 plus 160 times 0, that is 1,200. Okay, and the next one, if we have that 0, 8, so 240 times 0 plus 160 times 8, and the total of that is 1,280. Okay, that is 1,280. And then lastly, for 2.5, 5, so we have 240 times 2.5 plus 160 times 5. Okay, and identifying its product and the sum, we have 1,400. We have 1,400. So, if you will recall, the value of x here indicates the number of coffee tables. And then y indicates the number of n tables. And then z indicates the maximum profit. So, comparing the 4 points, we have here z is equal to 1,400 as the highest. Okay, compared to the other profit of the other three corner points. So therefore, we can say that we can have this conclusion. The maximum profit that is possible when the craftsman makes 2.5 number of coffee tables and 5 end tables, yielding to a profit of 1,400 pesos. So this is the value of x, and then this is the y. And our z here is the maximum profit. Okay, which is 1,400. Okay, so take note, though that we are after with the real life solution for this, There's no problem if our answer is not a whole number. Okay? It's fine. Though that we have here 2.5 as the quantity of the coffee tables. That's fine. Okay? As long as it is not negative. Because our goal here is how to maximize the profit. Okay? So it's fine. Okay, it's fine if you have a decimal. Okay, if you have a decimal for your two independent variables. Okay, as long as it will satisfy the given condition. Okay, to have the conclusion again of this problem, the maximum profit is possible when the craftsman makes 2.5 number of coffee tables and 5 end tables, yielding to a profit, okay, the maximum profit of 1,400 pesos.